Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to implement Deep Q-Learning in Theano for Breakout. Since we've already implemented Deep Q-Learning for Cartpole, all that's really required here is that we're changing the network from a feed-forward neural network to a convolutional neural network, and we're stacking multiple observations to create the state. If you don't want to try to code this yourself, although I highly recommend you do, the relevant file in the course repo is dqntheano.py in the subfolder Atari. At the top, we have all our usual imports. Next, we define image width and height as constants. This will be used for downsampling the images. Next, we have the initFilter function. This helps us initialize the filters for the convolution layer. Next, we have the convPoolLayer class. This doesn't actually do pooling, it's just a legacy name from before. So inside the constructor, we take in the input size, the output size, the filter size, which will be a square, and the stride, which will also be a square. Inside the constructor, we initialize the weight matrix, the bias, we set the strides in the params, and the activation function. In the forward function, we do a convolution with the weight matrix, add the bias, and then pass it through the activation function. Next, we have the downsample image function. It takes in an image, crops it, scales the values to be from 0 to 1, converts it to grayscale, and then resizes it using nearest neighbor interpolation. Next, we have the hidden layer class, which is exactly the same as before. Next, we have the DQN class. Most of the changes here will be in the constructor. Notice how we no longer have to specify D, because we know the image size and we have to add the convolutional layer sizes as an argument. At the top, we have some hyperparameters. We have to cast these to float32s because Theano's convolution function is very strict about the types you put in, so you'll see some extra casting around this script due to that. Next, we declare the inputs and targets. This is mostly the same as before, but now X is a 4-dimensional tensor. After that, we start to create the graph, first with the convolutional layers. Remember that in Theano, things get kind of messy because you have to manually calculate the size of the image after the final convolutional layer so that you know what size the weight at the next layer will be. Instead of trying to calculate it manually, we'll be passing in a dummy input instead. This allows us to avoid any errors that we might make in our own calculations. Next, we build the fully connected layers. After that, we collect all the params. This is useful for both copying the network and for specifying the updates. After that, we specify the cost and the updates and compile the train and predict functions as usual. In this script, I've used an alternative way of storing the experiences, which is perhaps more intuitive, a list of 4 tuples. You'll see how we can split up the tuples later. Next, we have the copy_from function, which is the same as before. Theano provides us with useful setValue and getValue functions. Next, we skip over to the train function, which is now different because the way we've stored the experiences is different. First, we can make use of the built-in Python random module to take a sample from the list. Next, we need to separate the tuples. We can use zip for this. We then map each list of tuples to NumPy arrays since they are most useful in this form. Finally, we calculate the targets and call the train op. Next, we have the addExperience function. Notice how it's a lot simpler than before, since now we can just append the tuple itself. Sample action is the same. Next, we have the updateState function. This takes in a state, which is a list of observations of size 4 or less, and a new observation. It appends the observation to this list, and then removes the first observation if the list is greater than size 4. Remember, this is because we represent the state as 4 stacked consecutive frames. Next, we have the play1 function. This is a little more complicated than before, but only because we now have to worry about stacking the frames to build the state. Before the loop, we add the initial observation to the state. Once we're inside the loop, we need to take an action. But we don't have a full state matrix to pass into the model for the first 3 iterations, so all we do is sample a random action. Next, we copy the most recent observation to the previous state list. This is analogous to copying the observation to the previous observation in our earlier code. Next, we perform the action and then add the resulting observation to the state. We then update the rewards, call train on the model, and then update epsilon. Remember that we are now using finer grain detail on the epsilon update, decreasing it linearly until we hit 0.1. Finally, we check if we should copy the main network over to the target network. Next, we have the main function. This is mostly the same as before, except we have some additional hyperparameters, specifically the convolutional layer sizes. Other than that, nothing in here should be unexpected. Let's run this and see what we get.